Hey there, y'all. Today we're going to look at 1.6 on transformations of exponential functions. In this section, you're going to be able to identify the effects that the graph of the functions by replacing f of x with f of x plus k, f of x minus h for positive and negative values, and then also with a of f of x, and then f of ax, negative a of f of x, and f of negative ax. And so one thing to know about these different types of transformations is that once we understand these rules, they are good for any other type function that we'll look at. So when we talk about quadratics, or we talk about higher powered functions, or we talk about, if you go to pre-calculus and we talk about trig functions, all of these rules still apply to all of these types of functions in the end. And so these two standards that we're looking at, comparing properties of two functions given in different representations, and also describing the effects of the transformations as given, finding the value of k for the graphs. And so we're going to look at a couple definitions first, and then we'll get into a couple of the examples. And so let's look at those definitions. First definition is the parent graph. The parent graph is the graph of the parent function, and the parent function is the simplest function of the family of functions. And so when we talk about like a linear function, like a line on the coordinate plane, right? So we could talk about how the parent function there is just the line y equals x with a slope of 1 going through the origin. But that line can be translated up or down. It can translate left or right. It can be dilated so that the slope becomes steeper or less steep. It can be reflected so that it has a negative slope. And we're going to look at those transformations for exponentials. And so with exponentials, when we talk about the parent function, it's not just one exponential function we're talking about. It could be for any base. So y is equal to b to the x. And again, b being any valid base, which means it has to be positive and cannot be equal to 1. And so there's three types of transformations we're going to talk about. And that includes being able to slide the graph, reflecting the graph about an axis, or dilating the graph. And so the first transformation we're going to talk about is translation. A translation is a transformation in which a figure is slid from one position to another without being turned. And so we can slide horizontally, or we can do a translation vertically. And we're going to look at both of those in these first two examples. So let's look at those. In example 1, we're going to describe the translations that happen in y is equal to 2 to the x plus 1 as it relates to the parent graph, and we're going to graph this function. All right, so first off, we need to know what the parent function is for this. And so we have x, and we're going to do 2 to the x to see the parent function. Then talk about what that plus 1 is going to do. And so if I use negative 1, 0, 1, and 2, we're going to find those values. And so 2 to the negative first, remember that's going to take it and find its reciprocal, so 1/2. 2 to the 0 would be 1. 2 to the first is 2. And 2 squared is 4. And let's take it one more step. Let's go to 3. 2 to the third is 8. And so we'll plot those 5 points on the coordinate plane. Negative 1.5, 0, 1, 1, 2, 2, 4, and 3, 8. And so we have those 5 points there. Now, normally we draw the line, but these are just temporary points because we're going to take these points and they're going to shift. And so we want to talk about what happens when we add this 1 here. And so if I do 2 to the x plus 1, plugging in those same x values, what happens? Well, I get 2 to the negative 1 plus 1, which is 2 to the 0. Well, 2 to the 0 is 1. And so that point is now here. So at negative 1, I'm now at 1. And then when I do 2 to the 0 plus 1, we get 2 to the first, which is 2. So we're here. 2 to the 1 plus 1 would be 2 squared, and that's 4. So we'd be here. 2 squared plus 1. So that's going to be 2 to the third, which is 8. So I'm now at 2, 8. And then when I do 3, 2 cubed plus 1, so that's 2 to the fourth, that's 16. And so I'm off the top of the graph. And so when we talk about where these points are going, yeah, we can talk about how the red dot looks like it goes up to the blue dot, right? Well, is that gap the same every time? Well, get us shifted back here. When we look at the distance between these 2 points, between a half and a whole, that's only a half. And then between this red dot and this red dot is a whole unit. But between this dot and this dot is 2 units. Then we get 4 units between these. And so what we see in the end is the gaps aren't the same. But if you look left to right, look at the gaps here. From the blue to the red is 1 unit. Blue to red is 1 unit. Blue to red, 1 unit. Blue to red, 1 unit. And so going from the red to the blue, we've shifted which direction? We've shifted all these points to the left 1 unit. And so when we see this plus 1 in the function here, or up here, what this has done is it's shifted the graph 1 unit to the left. And so we're going to scroll down here and we're going to actually look at the table towards the bottom of the notes here. And so go to the bottom of your notes and we're going to start filling out this table. So let's look at that. So here's the table that's going to summarize everything that we're looking at with transformations. We're going to first look at horizontal translations because that's what we did in example 1a. And so in example 1a, we saw we had our function, our parent function of 2 to the x. That was those red dots that we put on the graph. But then we did 2 to the x plus 1. Now, how does that come into play? Well, it's actually going to be a subtraction of the h that happens. Because when we have this value, it actually lies to us. Think about like an ex-boyfriend or ex-girlfriend. What do they do to you in the end? They eventually lie to you, right? And that's what happens here. So something that's directly attached to the x, like the plus 1 in this case, it's going to lie to you. And something we want to remember is that the x lies to you when it touches the x value. And so if the graph is going to shift to the right, our h value is going to be positive. But when we see it in the function, we're actually going to see x minus something. So we're going to see something like 2 to the x minus 5. That would shift us to the right 5 units. And if I see h is less than 0, that means I'm plugging in a negative value. But I'm plugging in a negative value to another negative. There's that minus sign there. And so we end up with like 2 to the x plus 1, like the example that we had. And so that is what we're looking at with horizontal translations. We're going to be talking about the opposite of what our eyes are showing us. If it's moving to the right, we're going to be seeing a minus sign in this part of the formula. If it's a plus sign there, we're shifting to the left. Remember that the x is lying to you. Let's go back up and now look at example 1b, where we're going to talk about vertical translations in a graph. In example 1b here, we're going to describe the translation that happens in y is equal to 3 to the x minus 4 minus 3 as it relates to the parent graph, and then we're going to graph this function. And so we talked about in the previous problem how that part of the exponent, right, the minus 4 here, remember that part's going to lie to us in which direction it's going, but it's always going to be in the horizontal direction. And so that minus 4, again, makes us think that we're going negative, which makes us think to the left, but it's lying to us, so it's really going where? To the right. And so we know that this will be a shift to the right 4 units from whatever the parent function is. Now, the minus 3 out back is going to be a vertical shift. And so when we see the value there, it's not attached to the x. And so it's going to shift us whatever it tells us. So if it's minus 3, it's shifting us down 3. Had it been a plus 5, it would shift us up 5. Because again, it's not attached to the x, so it's not lying to us, it's telling us what direction it's going. And so the minus 3 here will shift down the graph 3 units in this case. And so let's see what that does to the parent function. And so my original function would be 3 to the x, and again using negative 1, 0, 1, and 2, we get 3 to the negative first, which is 1/3, and 3 to the 0, which is 1, and 3 to the first, which is 3, and 3 squared, which is 9. Yeah. And so we're going to now plot those 4 points. And so -1 and 1/3, 0 and 1, 1 and 3, sorry about a jump in there, and 2 and 9. And then we're going to take these 4 points and shift them right 4, down 3. And so let's start with the point at the top. Right 4, down 3 will get us here. From this point at 1, 3, we'll go right 4, down 3, and we end up at 5, 0. From here, right 4, down 3, we'll end up at 4, -2. And be careful with this one that's already between two integer values. But again, we're going to go right 4, so it ends us up at +3. Then down 3 will end us up between -2 and -3, and actually it'll be -2 and 2/3. And so we see those 4 points, but the shift downward also affects our asymptote. And so our original asymptote would have been here at the x-axis coming across through here. But when we shift that graph down, asymptote goes with it. And so we're going to see that our asymptote is now down here at y equals -3. That's our asymptote. And so our line itself is coming through these 4 points and then getting closer and closer to -3. But again, we'll never become -3. And so if we talk about the range, because remember the domain is all real numbers, the range here actually shifts. Instead of being from 0 to infinity, it's now, sorry about that, let's get that shifted back over. We're now from -3 to infinity. Because again, that acts as our bottom for this graph. And so let's go back down to the table at the end and we'll look at vertical translations and how they are summarized. Talked about with our horizontal translations, our vertical translation is going to be of a similar fashion. So if our f of x is 3 to the x, or whatever base it might be, that vertical translation is going to attach itself as k on the back of the function. And so we're going to get 3 to the x plus the k value. And so, again, if it's +5, we're going to go up 5. And so if k is greater than 0, this will shift the graph up that many units. And if the k is less than 0, that's going to shift our graph down that many units. And so, again, it's not attached to the x, so it's not lying to us. It does exactly what it says in the vertical direction every time. And so as you see on the table, the next type of transformation we're going to look at is reflections. And so let's go back up to example 2 and look at those in the notes. So reflections, what they're going to do is flip a figure in a line called the line of reflection. Now, we can put a line of reflection anywhere on the coordinate plane, but for our purposes of what we're doing, there's 2 places that we're going to put that line. It's either going to be along the x-axis that we reflect this, or along the y-axis. And so if I have that line of reflection here, that means I'm flipping this graph, anything that's above the x-axis, to be below the x-axis. Or if this graph were below the x-axis, it reflected above. And we can also reflect things across in the vertical sense. And so if I have a line of reflection on the y-axis, anything to the left will reflect to the right. And anything on the right would reflect over here to the left. And so we will see what those points do in this graph. And so let's look at example 2a. We want to describe the reflection in y is equal to -4 to the x. And pay attention here, the negative is not inside the parentheses. It is out in front. Because remember that the b value, the part that's being raised to the power, has to be positive. So we're not going to change that base to a negative. But let's see what it does to our values as we look at this table. And so our parent function is 4 to the x. And so -1, 0, 1, and 2. And so we're going to get 4 to the negative first. That's 1/4. 4 to the 0 is 1. 4 to the first is 4. And 4 squared is 16. But when I put that negative in front, Remember, order of operations would make this happen after we do the power, and so doing -4 to the x, again, the negative being out in front, it's going to take all of these values and make them negative. And so we get -1/4, and -1, and -4, and -16. And so where this reflects it is across the x-axis. It's taking all my y values from being positive to now be negative, so my curve's going to sit down here. And so let's look at what happened to the original points and where they're going to go. And so -1 and 1/4. 0, 1, 1, 4, and 2/16 would be way up here. But again, that negative in front is going to reflect it across the x-axis. And so all 4 of these points will end up below the x-axis the same distance. And we see that here with these 4 values. 1/4 to -1/4, so that's going to go here. And then 1 to -1, so that's going here. 4 down to -4, and 16 down to -16. And so our final graph is this blue graph now that is below the x-axis, like we talked about in section 5 actually, where we saw a couple with a negative out in front there, and these graphs were below the x-axis. And so, for example, the range on this type graph, again, we're below the x-axis, and so our range here would go from what? -infinity up to 0. And so what is the transformation here? The transformation is a reflection across the x-axis. And again, that's a vertical reflection. And so sometimes we'll put that out front, that it's a vertical reflection. But reflecting across the x-axis gives us the information that we need. And we want to know that we're changing the y values of these points. The x values did not change. Like this point here is the one that reflected down, right? The point at 1, 4 became 1, -4. Okay, so let's look at example B and look at how reflection works when we reflect it across the across the y-axis instead. So let's look at example B. We've got 4 to the -x in this case. And so we've got those same 4 values for our parent function that we had in the previous example. -1, 0, 1, and 2. And 4 to the -1st is 1/4. And 4 to the 0 is 1. And 4 to the 1st is 4. And 4 squared is 16. But when we put that negative up in the x, that means whatever value I'm putting in for x, I'm actually getting its opposite. And so we're getting 4 to the negative first, but a double negative becomes what? Positive. So this is really 4 to the first, which is 4. And then I get 4 to the -0. Well, there is no -0, right? The opposite of 0 is still 0. So 4 to the 0 is still 1. 4 to the negative first, because the negative sign and then the 1, that's going to give me 1/4. Then 4 to the -2nd will give me 1/16. And so plotting the original points, so I'm at -1 and 1/4, 0 and 1, 1 and 4, 2 and 16. When we reflect those points across the x-axis, this point is now coming over here. This point, sorry, across the y-axis. The point on the y-axis is not going to move because if it's already here, how can it reflect anywhere? It's still here. This point here at 1/4 will now be at -1/4, and this point at 2/16 is now over here at -2, +16. And so our final function is this decay function. And that actually makes a lot of sense because remember that a negative exponent does what to its base? It takes the fraction and does what? Flips it. And so that would just give us a base of 1/4, and remember that would make this now an exponential decay function, and that's what happens when we have that negative exponent. And so we get that switch in place. The asymptote is still on the x-axis here. It did not move because reflecting the asymptote horizontally this way keeps the asymptote where it was. Okay, and so what is the transformation here? This is a reflection across the y-axis, and again, this would be in the horizontal direction. We'll rewrite that so it looks a little better. Horizontal. Okay, so again, this is a reflection across the y-axis. Okay, so let's go down to the table and look at those two examples. Look at the summary down there. So let's talk about reflections. The A value is going to be in one of two places. When we talk about a horizontal translation, that A value, remember horizontal is moving across the y-axis, and so that A value is going to be attached, or the negative sign is going to be attached to the x. And so we're going to see it like 2 to the negative x. And again, that's what's going to be reflecting horizontally to move those values there. When we do it vertically, remember that's shifting these values in the vertical directions, it's our y values. We're going to see that negative out in front. And so we would see it as the negative 2 to the x. And again, we could have other transformations going on. This, if the negative is not in a grouping symbol or outside of any grouping symbol, the graph is reflected across the x-axis. Again, this is going to be our vertical translation. And if the negative is inside a grouping symbol, the graph is reflected across our y-axis, giving us our horizontal translation. And so we're looking for it in one of those two places. All right, and so the last thing we're going to look at is dilation factors. And so we're going to go back up to example 3 and look at what the dilation factor does to the graph. Right here, we're going to describe the dilation that's happening in y is equal to 1/2 times 3 to the x. And so that 1/2 that's out in front, let's see what it does when we multiply it to these other values. And so we're coming back to a parent function that we've used before, 3 to the x. So using -1, 0, 1, and 2 gives us 3 to the negative first, that's 1/3. 3 to the 0 is 1. 3 to the first is 3. And 3 squared is 9. But now we're multiplying all these by 1/2. And so when we put in that 1/2 times 3 to the x, again, the order matters. We're doing the exponent first, then multiplying by 1/2. We're taking all of these values and multiplying them by 1/2. And so we end up with 1/6, 1/2, 3/2 or 1.5, and 9/2 or 4.5. And so we can plot those points. Again, the originals, we'll do those in red. The original points would be at -1 and 1/3, 0, 1, 1, 3, and 2, 9. And all of those points have been shrunk down by 1/2. And this is a vertical dilation here because our y values have changed. We're going down to 1/6, and so that's halfway between. We're going to 1/2. We're going to 1.5. We're going to 4.5. And so our final function is this orange one. Let me redraw that. We're going to do the orange one. Oops, not what I wanted to hit. Hold on. Draw our line connecting these 4 points, coming up like so. And so again, this graph has been squashed in half. If this value was larger than 1, it's actually going to stretch it because let's say we multiply all these by 5. We'd be at 5/3 and 5 and 15 and 45, and these values would just get huge even quicker than what they already do. Let's look at example 3b really quick here. And so in this one, we see that the fraction is up in the exponent. And so our parent function is 5 to the x in this case. And so -1, 0, 1, and 2. And so getting these values, 5 to the negative first is 1/5. 5 to the 0 is 1. 5 to the first is 5. And 5 squared is 25. And so with those 4 values, now we have this 1/2 power. And so remember what that's going to do when we do the 1/2 power is that we're going to actually have to multiply the power first and then do the exponent. And so we're going to get 5 to the -1 times 1/2. And so it's 5 to the -1/2. So there's a negative exponent going on. There's a square root going on. This is going to become a decimal here. because what's happening with this value is it's actually changing. So we're going to get the 1/5, and then remember that's to the positive 1/2 power. It's the square root of 1/5. That is such a small number. It's actually going to be bigger because when you take a square root of a decimal, it actually gets closer back to 1. So it's actually going to be a little bit bigger. But let's go 5 to the 0. Well, timesing that by a half, we're still 5 to the 0, so we're still at 1. 5 to the 1/2 times 1, and so that's going to give us 5 to the 1/2, so that's the square root of 5, and then doing 5 to the 1/2 times 2, that's 5 to the first, which is 5. And so let's come up and talk about these two decimals. The square root of 5 is approximately 2.4. Again, you can go to your calculator and get the exact value, but it's about 2.3 to 2.4. And then the square root of 1/5 is about 0.4. And so again, you can double check the calculator and get that value of what it's going to be. And so we'll graph those. So we're at -1 and 0.4. And then we're at 0 and 1. And we're at 1 and 2.4. And so that's going to be about here. And we're at 2 and 5. And so what's actually happening, and we don't see it with the original function, but this is actually a horizontal dilation. We're actually taking values and squashing them this way, because what's happening, or actually in this case, we're actually expanding out because the value is smaller than 1. It's actually an expansion. The value of this point at 5 would have been at 1, because it should have been here, right? This value of 5 is now not at 1, it's at 2. And so we see that it's changed. And then same thing here, if we go on to -2, we would get this that smaller value as well. And so when we graph those 4 points, we're looking at this here. Okay? And so those are the 4 points that we have there. All right, so let's quickly look at the bottom here and look at our final part of the table. And so our dilation, remember, if the A is outside of any grouping symbol, the dilation is vertical. And if the A is inside the grouping symbol attached to that X, oops, it's not writing for me. If it's inside, the function is dilated horizontally. And again, it's inside with the X, and so it's lying to us. And the lie here is that it is the reciprocal of the value that's the dilation. So in this case, that 1/2 is actually a stretch by a factor of 2. And so it's going to multiply those X values by 2 in the end. And so that's what we're looking at there. I've got example 4 here. We're going to look at those in class. But if you got questions on those, especially if you're not in class, we can look at those examples one-to-one. So if you got any questions, let me know, and I'll catch y'all next time.